random walk on random maps.
Okay, thank you. So today what I'm going to do is I'm going to talk about something slightly different. So I'm going to talk about the Tut embedding of the mated CRT map. And before I go into this, let me just quickly recap what I've been talking about. So the general idea is that if you have a random walk problem on a random planar map, then what I've tried to explain is that you can always convert this into a question about random walk on the mated CRT map. You have this sort of canonical model of a random planar map that you can analyze. And the reason that you can analyze this is that this in turn converts the question into something about space-filling SLE on Liouville quantum gravity. Okay? And when you analyze this question in the context of space-filling SLE on Liouville quantum gravity, then really what you're doing is you are looking at random walk in random environment. So you have a random walk in random environment problem, where here the graph that you're looking at, this is something which corresponds to chunks of space-filling SLE. Okay, and so now what I'm going to do is I'm going to talk about an embedding that you can define from random walk, and this is called the Tut embedding. And you can define the Tut embedding in different contexts. The sort of nicest setting to talk about the Tut embedding is when you're working with a planar map with the topology of the disk. Let's say I have a planar map M, and I'm going to assume that it has the disk topology. Okay, and how is this embedding going to be defined? So let's say I have my planar map here, and it has boundary. Then what I'm going to do is I'm going to enumerate these boundary vertices. So let's say this is y1, y2, y3, y4, etc. And I have something, perhaps a random triangulation here. And I'm going to assume that I have some marked vertex on the inside. Let's call this vertex x. And under the embedding map, under the Tut embedding, I'm going to be mapping my planar map to the Euclidean disk, and this vertex x is going to get mapped to the origin. And the way that it's defined is that I'm going to let, for each j, I'm going to let p sub j be the probability that a random walk starting from my special vertex x exits probability my random walk exits the map in the interval from y1 up to yj. Okay, so p sub j is just the harmonic measure as seen from x of the boundary interval, which starts from y1 and makes it to yj. Okay? And once you have these pj's, these are going to determine for you how you're going to embed the boundary. Okay, so I'm going to take y sub j, and I'm going to send it to the boundary point e to the 2 pi I pj. Okay, so this defines the map on the boundary, and then for the other vertices in the interior of the map, I'm going to define my map by making it be discrete harmonic. Okay, so it's just going to be the discrete harmonic extension of these boundary values. Okay, so this is the Tut embedding, and this is what I'm going to be looking at, because this is the one which is most connected to random walk on the vertices of the planar map. This is how it's defined in the disk topology. There are other ways of generalizing this, which I don't really want to describe in too much detail, but you can generalize this to planar maps with other topologies. For example, it's not very difficult to come up with ways of doing this to the setting when you have a planar map with, say, the topology of the, let's say, the sphere or the plane. Okay. Okay, so this is what I'm going to talk about. And what is the theorem? So the theorem, and this is with Ewan Gwynn and Scott. And what it says is that if you take the Tut embedding of the mated CRT map, and here, whenever you talk about the mated CRT map, there's always a parameter which is floating around. And in this case, I'm going to assume that my parameter, which again describes the correlation between the two coordinates of the encoding Brownian motion. So I'm going to assume that this is minus the cosine of pi gamma squared over 4, okay, where gamma, this is the Liouville quantum gravity parameter. So the theorem statement says that this Tut embedding, this converges to gamma Liouville quantum gravity decorated by a space-filling SLE kappa. Okay, and so what does this mean? So this means that if you take the natural measure associated with your planar map, then the measure, after performing this embedding, is going to go to the gamma Liouville quantum gravity measure. And the mated CRT map always has associated with it a distinguished path, and the other part of the theorem is that this path is going to go to an independent space-filling SLE path. Okay. So this is the theorem, and before starting to talk about how this is proved, let me make a few remarks about it. The first one is purely a kind of Gaussian free field type remark. So this is something which is very common in the Gaussian free field SLE framework. In particular, in the mating of trees, there's an abstract theorem that says that if you take your SLE on top of a Liouville quantum gravity surface, so there's a theorem that says that this is a measurable function of the Brownian motion pair x and y, which describes the evolution of the boundary length of your SLE. But the point is that in the mating of trees, this is actually a non-explicit function. Okay? So this is not explicit. And this is something which is, again, it's very common in these constructions where you look at things like SLE on top of the Gaussian free field, and you want to show that something is a measurable function of the Gaussian free field. So usually when this is proved, you never exhibit exactly what the function is. And in the mating of trees, there's an example of this where we want to show that the sort of pianosphere Brownian motion, which encodes the space-filling SLE on top of the Liouville quantum gravity, actually can produce these two things in a measurable way. But when you use this theorem, this Tutt embedding, this theorem actually makes the function explicit, because it is just what you get when you take your Brownian motion pair, construct the mated CRT map, and then Tutt embed that. Okay? The other remark, or one other remark I want to make, is that this is a result about this particular random planar map construction, the mated CRT map, but this actually gives embedding convergence results for actually many different types of discrete random planar map models. Okay, and this works for any type of random planar map model for which you know it's converging to the mated CRT map in this pianosphere sense. And this includes, for example, if you have a random planar map with the uniform spanning tree on top of it, or an FK decorated planar maps, also the UIPT, or if you have a map with a bipolar orientation, or a Schneider-Woods, etc. And I want to take a moment to explain exactly what this kind of statement means in practice. Yep.
Yeah, just a comment about your first remark. So this means that the theorem holds in the almost sure sense. Is that?
Yes. Yes, that's right. Yeah. Yeah. So it's going to be a quenched invariance principle. So it's going to hold in the almost sure sense. So I want to take a moment just to explain in what sense you get an embedding result for actually for discrete random planar maps. For example, you can imagine that you have, let's say, a UST decorated planar map. So just imagine, for example, that this is somehow sitting in the background. And in order to use this continuum embedding result, in order to embed your UST decorated planar map, what are you going to do? So you can pick some vertices in your map. Let's say I've picked these 5 vertices, and then what you can do is from each vertex in the map, you can draw the branch of the spanning tree and also the dual tree. Okay, so you're going to get a picture which perhaps looks something like this. So I'm going to make the spanning tree branches in green and the dual branches in red. Okay. So what this is going to do is it's going to divide your planar map into this collection of cells. Okay, and each cell, depending on how many points you choose, is going to contain some number of vertices. Okay, but you have this this kind of picture where I've taken my my planar map and I've coarse grained it by dividing it into these cells, which are separated from each other by branches and dual branches of the spanning tree and dual tree. So you have this collection of cells, okay? And the way that you can embed this discrete random planar map model is you don't do the Tutt embedding, at least at this point, on the vertices of the map itself. Rather, what you do is you do the Tutt embedding. So you do the Tutt embedding of the graph of cells. Okay, so And the point is that the pianosphere convergence, the convergence of the contour functions of your discrete random planar map is going to tell you that these sort of mesoscopic cells are going to converge to the graph that you get from the mated CRT map, and therefore an embedding result that you prove in the continuum, in particular this theorem, is going to apply here. Okay? So this is going to go to Liouville quantum gravity plus SLE. Okay, so you get these sort of coarse-grained embedding results for many different types of random planar map models. Okay, so now what I want to do is I want to tell you a bit about how this result is proved. Yep.
In your theorem, when you want to do it for the topology of the disk,
yes.
What adaptation do you have to make to your correlated Brown?
Oh, so okay. So basically, let me quickly explain that. So the way that it works is that you have sort of three different settings. So you have the sphere, and for the sphere setting, your correlated Brownian motion is just going to be a Brownian loop, which comes back to the origin. And you have the disk setting, and in the disk setting, you're going to have a correlated Brownian excursion, but it's going to terminate somewhere here. And then this length determines the boundary length of the disk, and the length of the Brownian excursion itself, this determines the area. And then the whole plane topology, this is just a Brownian motion, just a normal Brownian motion. You don't have to consider a Brownian excursion. Okay. Okay. So.
So, Jason, can I
Yep.
ask about this? When you want to get embedding convergence results for the actual planar map models,
Yes.
planar map models. So you do this coarse graining thing.
Yes.
But what you're embedding, is it actually just a portion of the map, or is it the whole map itself when you do?
Well, I mean, the way that you define it is, so inside of each one of these cells, you're going to have some number of vertices. So you could have, depending on what setup you have, you'll either have a polynomial number of vertices or a logarithmic number, and you're just going to map them all to the same point. But somehow, when you take a limit, that's going to wash out, and you won't see.
So there's a choice to be made, but it doesn't really matter so long as kind of the number of vertices per cell tends to infinity, roughly speaking. Or?
Yeah, I mean, so actually, I mean, the way that it's sort of exactly done the way that sort of exactly follows from what we've done is that you need, let's say that your map has n vertices to begin with, then you have to make each one of these cells have the same size, and the size of the cells, so sort of how small you can take them, depends on how strong your convergence result is for the pianosphere sense. So if you're in a regime like for a bipolar-oriented map where you can do the strong coupling, then these cells will each have a polylog number of vertices. But for other settings, like for the FK model, you would have to take a power then. Okay, so this. So one other remark that I wanted to make is that this this paper, which does this has actually been on the archive for a bit over a year now. So there's an archive version of this paper, and the archive version of this paper is proving a kind of invariance principle for random walk on top of, where the random walk in random environment where you're using space-filling SLE chunks as your environment. And so this archive version is actually using a lot of model-specific features of SLE on Liouville quantum gravity. So in particular, the fact that SLE is conformally invariant actually comes into it, and it's something which is very important. But since then, there's been a new version of this, which has been in the process of being written over the course of this last year, which will hopefully go up on the archive next week. And the new version of this doesn't really use any model-specific arguments anymore. So it's just going to be a general random walk and random environment type statement. And I want to explain to you how this works, because it's a little bit different than the usual invariance principles that you see in the random walk and random environment literature. So I want to just spend a moment giving you an exact definition of the setting in which we're going to be working on. Okay, so in general, we're going to have something which we're going to call a cell configuration, and this is what's going to be part of what determines our environment. And this is always going to be planar, so these are going to be two-dimensional results. And a cell configuration is a collection of cells. And a cell is going to be a set which is compact and connected. And we're going to assume that the cell configuration is locally finite. And we're also going to assume that the intersection of any two cells, this has a zero Lebesgue measure. So this is just to avoid certain pathological issues. And then we have to put kind of a graph structure on this cell configuration. So you can imagine this is just some kind of partition of the plane. And the way that you do that is there's going to be an adjacency relation. Which I'm going to call, or I'm going to indicate with a tilde. And the adjacency relation, it has the property that if you have two cells which are adjacent, then it has to be true that they have non-empty intersection. And they're also going to be distinct from each other. And then you have to decide kind of how fast your random walk is going to move. And so there's also going to be a conductance, C, and C is defined on adjacent cells, and the conductance has to have the property that it's going to be positive and symmetric. Okay, so it's positive on adjacent cells. So this is for H and H prime, which are adjacent. Okay. So in the back of your mind, again, the thing that you should be imagining is that you just have some kind of partition of the plane. For example, with space-filling SLE chunks, or there are also lots of other sort of natural options. For example, you could just take the squares associated with the usual integer lattice, and they will satisfy all of these hypotheses. Yep.
Then the neighbors will also be diagonally, right, on the lattice?
No, they don't.
Definition.
No, so the adjacency relation just says that if they're adjacent, then they have to have non-empty intersection. But they don't, it's not equivalent to having a non-empty intersection.
So how do you?
You have to specify. It's part of the data. So you have the collection of cells as sets. You tell me what the adjacency relation is, and then you tell me what the conductance is.
You share a point, only your point.
No, so I understand. So that's the question. But the answer is you specify to me. So you tell me what is the adjacency relation. That tells me whether or not sharing a point is going to be sufficient or not for them to be called adjacent. So you make that choice. This is actually a very important thing that comes up in the SLE stuff, because SLEs can intersect each other in sort of complicated ways. They can intersect, for example, along arcs. Sometimes they just have fractal intersections, and so it's kind of important to distinguish between these two cases. So this is just part of the data. Okay, so what are the assumptions? So the first one is going to be a translation invariance. And in usual random walk and random environment, this is the kind of assumption that you make. But here, what's going to be different about it is it's going to be translation invariance only modulo performing a rescaling. Okay? And it turns out that there are actually a number of different ways of giving a mathematically precise definition of what one could mean by translation invariance modulo rescaling. One very convenient way to do it is that you can say that something is translation invariant modulo rescaling if it arises as a limit of finite cell configurations which are centered at a Lebesgue typical point. Okay, so what this means is that if you have a cell configuration H, okay, then what you want is that if you have a sequence of cell configurations, Hn, these are your finite cell configurations, and then you center them at a Lebesgue typical point, then what you want to say is that up to a rescaling, these guys are converging to your limiting guy. Okay, so you want this converges to this up to this choice of scaling factor. Okay, so this is translation invariance modulo rescaling. The second one, this replaces the usual ergodicity assumption that one makes when one does random walk in random environment. And this is ergodicity modulo rescaling. And what this says is that if you have a measurable function, so every measurable function f of your cell configuration, which is invariant modulo rescaling. And what this means is that if you apply your function f to your cell configuration after it's been rescaled by some factor and then translated, okay, so up to this scaling factor c and translation by z, so what you want is that this is equivalent to your function applied to the original cell configuration. And ergodicity modulo rescaling means that if you satisfy these properties, then your function is going to be almost surely constant. Okay? And then the final assumption that one needs is the sort of non-degeneracy assumption. So this is kind of like, for people who do random walk and random environment stuff, this is sort of like you're going to play the role of your ellipticity assumption. And it kind of rules out things like cells being long and skinny. And it's going to be stated in terms of a certain moment bound. Okay, so this is the non-degeneracy condition. And what the non-degeneracy condition says is that if I define pi of a given cell to just be the sum over all cells which are adjacent to my given cell, I just take the sum of the conductances, then one part of the non-degeneracy condition is that the expectation of the diameter of a cell squared divided by its area. And here I'm looking at a particular cell. So H0 is the cell containing the origin. The origin containing cell. Then the non-degeneracy condition is that the expectation of the ratio between diameter squared and area times this stationary measure, this is going to be finite. And you also need another condition, which is that if you look at define a sum in the same way, but instead of looking at the sum of the conductances, you look at the sum of 1 over the conductances, then the other condition is that the expectation of the diameter of your origin containing cell squared divided by area times this pi star of h0, this also has to be finite. Okay? So again, the point of these conditions is sort of to rule out the possibility that you have cells which are too long and skinny. And they kind of have analogs in the random walk and random environment literature when you look at, for example, the random conductance model, because one condition that you can look at, for example, is you can require that your conductances have a finite first moment and also their reciprocals having a finite first moment. And this is sort of the same condition as that. And what does the theorem actually tell you? Yep.
You put any assumption of ergodicity on the conductance itself? I mean, I thought those are conditions on the cell configuration, not on the conductance.
The assumption on the cell conductances is that they have to be positive and finite for adjacent cells.
Some stationarity or nothing?
Oh, yes, so that's also stationary. Yes, right. Yep.
Stationary and ergodic.
Yes, yes, that's right. And actually, for the setting of the mated CRT map, they're just going to be equal to 1. So adjacent cells whose boundary intersects along a non-trivial arc are just going to have conductance 1. Simple random walk. And so what is the theorem statement? And this is the version which is going to be in the revised paper, which hopefully will appear early next week. So what it says is that if you have a cell configuration which satisfies the above hypotheses, and you have a random walk y, so y is a random walk on the associated graph with the associated conductances, then the following is true. There exists a covariance matrix sigma so that the conditional law of y given the environment, so given the cell configuration and the conductances, this almost surely converges to a Brownian motion with diffusion matrix sigma okay? And the notion of convergence here is modulo reparameterization. Okay? So you get the same kind of central limit theorem that you have in the usual random walk and random environment framework. So you have a quenched invariance principle to some Brownian motion. But because everything is only defined modulo scale, there's this issue associated with the parameterization. And so that's why this theorem statement is a modulo reparameterization statement.
Reparameterization is time reparameterization?
Sorry?
Time reparameterization?
Yes, time reparameterization, yes. Yep. Okay, so there are lots of different examples that you can apply this to. So for example, the simplest example is you do the usual random conductance model. Okay, so you just take your cell configuration to correspond to just the usual two-dimensional integer lattice, and you make the conductances between the adjacent squares. These are going to be IID conductances with well, it has to satisfy the non-degeneracy conditions. So, for example, you could assume that they are IID. And to make it very simple, you could assume that the conductances are always between epsilon and 1 minus epsilon. So this is one possibility. This is sort of the classical random walk and random environment framework. A more interesting example, perhaps, is what you get when you start to put Liouville quantum gravity into the picture. So for example, you could imagine that you have a domain D. So this is a domain in the complex plane. And you have your gamma Liouville quantum gravity measure mu h and a parameter delta, which is positive. And now to construct your cell configuration, what you do is you take the domain and you partition it into squares, into dyadic squares. And the way that you do this is you so you subdivide the domain into dyadic squares. And the property that each square has is that it's the first one, so that if you're sort of coming from the outside, where the mass of it goes below delta. Okay? So you subdivide it into dyadic squares, and each square has the property that its mass is below delta, and the mass of the parent, the dyadic parent of S, is bigger than delta. Okay? So this gives you a random cell configuration, and now you get a cell configuration where you can apply the theorem by picking a Lebesgue typical point. So maybe your point lands in here, and then you take a limit by sending delta to 0. Okay? So you center at a Lebesgue typical point, and you send delta to 0. But as you do that, you want to sort of be performing a spatial rescaling so that you get something non-trivial in the limit. And so you get some kind of an infinite volume version of this squared decomposition. This gives you a cell configuration which will satisfy the same set of hypotheses. Okay?
And here the adjacency of, how are the adjacencies defined?
Oh, so in this case, I mean, the natural thing to do is you would just define them. I mean, so you could do corners if you wanted to, but another option would be, and perhaps a more natural option, is you just say that two things are adjacent if they intersect a non-trivial arc.
But if you do the two definitions, will you get the same covariance or not?
So that's, yes you will, because in this case, they're just going to get the identity covariance, because this picture is going to have a symmetry, rotational symmetry. I mean, this
Doesn't it depend on how you do the dyadic thing?
well, it comes from the Liouville quantum gravity measure.
Yeah, but your dyadic partitioning, it fixes axis. It's not rotation invariant, right?
Means 90 degrees in that direction.
Yeah, so
90
it's just a
degrees,
90
but
degree
not-
rotational
it's not-
invariance.
That's sort of
Yeah.
enough to fix the.
Yep. Yes, so the covariance matrix is going to be a measurable function of the environment by ergodicity. Yep. Okay. And then the final version so this is the last version is just Liouville quantum gravity decorated by space filling SLE. Okay, and you know, one way of seeing that, you know, this is sort of this is going to work is, again, you can take a finite domain. You can imagine that you have your Liouville quantum gravity measure on it and your space filling SLE. And you can again pick a Lebesgue typical point Z and just zoom in around around that point. So this is actually going to be a little bit different from what I described before. So this is not the same thing as the usual mating of trees framework, because it's not exactly the same as a quantum cone, because you're going to be centering at a Lebesgue typical point and not a quantum typical point. But it's absolutely continuous in a certain sense. And so if you prove an invariance principle in this setting, you will also get an invariance principle in the original mating of trees picture. Okay? So the difference is that when you pick a point from the quantum measure, you're going to get a log singularity here. But if you just pick from the Lebesgue measure, you're not. And so this is going to be a slightly different setting than the mating of trees theorem.
Let's do a quantum cone.
It's another kind of quantum cone, but when I defined quantum cone before, it was implicit that it was a gamma quantum cone. Yep, so you just get a different type of quantum cone. Okay, so now let me say some words about how this theorem is proved. So in the random walk and random environment literature, there's a sort of strategy that you can use. So what is the random walk in random environment strategy? And one kind of very nice place to read about this, by the way, is that Merrick Biskup has a very nice survey article that he's written, which is in Probability Surveys. And I think it was published in 2011. And the kind of strategy is you define, you try to construct something which is called the corrector. So you construct the corrector. And what is the corrector? So this is going to be a function phi on well, in this case, it's going to be on our graph or our cell configuration. And this is going to be something which is discrete harmonic. And the reason that you want to construct this discrete harmonic function is that then if you apply it to your random walk, y sub j, then you're going to get a martingale. Okay? And once you have a martingale, you can apply the martingale central limit theorem to phi of yj to get that it's going to go to a Brownian motion. So this gives you convergence to your Brownian motion. And then the way that you finish is that you check that the corrector is going to be sublinear. So then you prove the sublinearity of phi. And what this means is you want to show that phi is very close to the identity. So phi of z minus z goes to this. So basically, sublinearity of phi of z minus z. Okay, so what you want is that this difference, this is little o of z as z goes to infinity. Okay? And the reason is that once you have that, then you know that then you can sort of combine these two things. Okay? So combining, you know that phi of yj, this is close to yj, or close enough, and if this is going to a Brownian motion, then that implies that this is also going to go to a Brownian motion. Okay? And in the usual sort of random walk and random environment framework, there's sort of a standard way of using the ergodicity of your environment in order to prove that the translation invariance and ergodicity in order to construct this corrector. So basically, what you do is you somehow, for the sort of standard method, so you somehow construct this this corrector phi, and you do it in such a way that if you look at the difference between it and the identity map, you construct it in such a way that its gradients are translation invariant and have mean 0. Okay, and once you've done that, then you're in great shape for proving that it's actually going to have sublinear growth, because then, you know, if you look at chi of, let's say, you're in the two-dimensional integer lattice, and you look at this function chi at let's say the vertex n comma 0, then this is the same thing as the sum j goes from 1 to n of chi of j comma 0 minus chi of j minus 1 comma 0, and this is now this is like an ergodic average, and therefore this is going to be little o of n as n goes to infinity. Okay? So this sort of tells you that on any given line, your corrector is going to have sublinear growth, and then you can combine that with harmonicity to see that the corrector itself has to have sublinear growth. So this is the usual strategy. And here, the way that it's going to work is the corrector is going to be constructed in a different way. And the reason is that we have a different type of translation operation to work with in this setting. So we don't have the usual translation, we just have translation modulo rescaling. Okay? So Okay, so the way that the corrector is going to be constructed here. So basically, what one wants to do is you want to define something kind of like the square lattice, but it should be somehow defined in a way which is translation invariant modulo rescaling. Okay, so you define a sort of lattice. And this is in the paper called a dyadic system. Okay, and this is done in kind of a careful way, again, so that you have the right sort of invariance modulo translations and rescalings. And what a dyadic system is it's a collection of squares in the plane, and it has the property that if you have any given square, S, which is inside of your dyadic system, then it has the property that the four dyadic children are also contained in the dyadic system. It also has the property that if you have any square which is inside of your dyadic system, then it has to be true that at least one of the four possible dyadic parents are inside of your dyadic system. And lastly, if you have any two squares, S1 and S2, which are inside of your dyadic system, then these have to have a common ancestor. Okay, a common dyadic ancestor, and so there's a particular dyadic system which is going to play the role of the random lattice, which you define on top of your graph, and this is called the uniform dyadic system. And this is all designed in a way exactly so that you can use the ergodicity and translation invariance modulo rescaling. So for the uniform dyadic system, what you're going to do is you are going to include inside, you first have to sort of choose a given square. Okay, so you're going to pick a scale. So let's say you pick some scale S, which is between 0 and 1, uniformly at random. So I'm sort of defining a base square right now. And you're also going to pick a center point, W, which is going to be uniformly at random in the square of side length 2 to the S, okay, which is centered at the origin, okay? And then you're going to take, in your dyadic system, the square S, which is equal to W plus this this square. Okay, so this defines one square inside of your dyadic system. So maybe it looks something like this. And then once you have this square, because every square inside the dyadic system, it has to include its children, all four dyadic children. It's sort of determined everything that's going to happen inside. So you know it has to contain the entire sort of dyadic subdivision of this square. And so in order to continue defining it, you have to sort of grow it out in the reverse direction. And the way that you sort of grow it out is that for this particular square here, you're just going to choose uniformly at random among the four dyadic parents of this guy and then choose to include that. So you have four possibilities. You can either include this guy, here, you have also this possibility, or this possibility. And what you do is you just choose one of these four options, okay, and then you just continue, and this will eventually define a dyadic system on the entire plane. Okay, so you sort of continue by choosing a random dyadic parent. Okay, and this gives you a kind of a random lattice. And the point is that for doing it in this particular way is that if you have a uniform dyadic system, then you can check that the pair, which consists of your cell configuration and your uniform dyadic system, this is also going to be invariant and ergodic modulo rescaling. Okay, and let me just finish by saying the last little bit about how the corrector is constructed. So what you do is you're going to start off with the identity map. So phi sub 0, this is like the identity map. So this is the identity map. Okay, so if you have a given cell, it's just going to map, you just choose some vertex in the cell and map it to itself. And then we're going to define a sequence of maps, phi sub m, and the phi sub m's are going to be what converges to the corrector. Okay, these approximations. And the way that they're defined is you have your lattice, your sort of dyadic system. So you imagine you pick some sort of scale, okay? And the scale that you choose for phi sub m is what you want is that the number of squares, the number of cells which live inside of here to be about m. Okay? So you have, in a certain sense, m cells, and phi sub m is just going to be the function which is discrete harmonic inside of the square. So let's say this square is S sub m, and it has identity boundary conditions. Okay? And so what one wants to do is you want to take a limit of these phi sub m's, and they're going to converge to this limit phi sub infinity. And the reason, very roughly speaking, why this works is that it's not difficult to check that the differences, phi sub m minus phi sub m minus 1, these are orthogonal in the the Dirichlet space here. So with respect to the Dirichlet inner product, and okay, so you have this sort of orthogonality property, and you also know that the sum of these increments, or let me just say, the sum of these increments, j goes from 0 up to n, for any n, of phi sub j minus phi sub j minus 1. These are always going to have Dirichlet energy, which is at most the Dirichlet energy of phi sub 0. Okay, because these are just like an orthogonal decomposition of the original identity map, and so you can control their Dirichlet energy. And once you have a series like this, where you can control the Dirichlet energy, then you can start to do things like bound the variation of the function along paths in kind of the same spirit that one uses the ergodic theory in the original, sort of standard random walk in random environment setting to boost this type of statement to a statement about the sublinearity of the convergence of the corrector and also the sublinearity of the corrector. Now, in the interest of ending on time for Jian, so that we can all go to lunch, I'll stop here.
Any questions or comments before lunch?
So you have a way to express sigma in terms of this integration?
Do we have an explicit expression for? Usually in these things, there's not an explicit expression.
So in your original, like if we're looking to see it, you need to show that sigma is certain kind, right?
Yeah, so I mean, in the situations that we actually care about, like SLE on top of Liouville quantum gravity, you have a priori rotational invariance of the underlying environment, and that automatically tells you it's a multiple of the identity. So that's not a major issue. But one issue which is actually unresolved in this work, and this is a very interesting open problem, is controlling the time parameterization. So of course, in all of these models that are related to Liouville quantum gravity, you want to prove that it converges to Liouville Brownian motion. And for that, you have to control the time parameterization, and that's something that we're not doing.
Okay, let's thank Jason for the series of lectures.